Let's say you want to find out the value of 2 to the power 5. Well, you just multiply 2 with itself 4 times. That is, 4 number of multiplications are required. In general, if you want to find out the value of a to the power n, you'll require n minus 1 number of multiplications. But can we do better? Of course, by using a technique called binary exponentiation, you can actually reduce the time complexity from linear to logarithmic. So what's the big idea? The idea is to represent the power in the binary form. Let's look at an example. 3 power 15. We represent 15 in the binary form, which is this value. We know binary form is equivalent to this value. We substitute the value in the power, and we know the formula a to the power m plus n is equals to a to the power m times a to the power n. We substitute the formula, we get this result. Now we just require 3 number of multiplications, which is way better. But the trick is, how do we find the values of 3 squared, 3 power 4, 3 power 8 in an efficient way? Well, we just find 3 and square it to get 3 square, and square the 3 square to get 3 power 4, and square the 3 power 4 to get 3 power 8. You get the idea. And in the end, we just multiply all the results to get the final result. Now, try to implement this in your own way. Before looking at the code, we are going to implement this in two ways. One is recursive and the other is iterative. Recursive is fairly simple because of its conquering and dividing structure, because we just divide the problem into subcases. In this case, we have three subcases. One is obviously base case. The base case is nothing but when a power is 0, any power 0 is 1, so we just return 1. And if power is not 0, and if it is an even number, we just divide the computation into two parts. First, we find the half of the power of the value and multiply it itself to get the full result. And if it's an odd number, since we can't just subdivide it into two perfect halves, we subtract 1 from it and calculate just like before. Since we removed 1, we multiply extra a here. So these are the subcases which we require for implementation in recursive. Let's go ahead and implement. I'm implementing this in Python, but you can basically do this in any programming language. We create a function called binary exponentiation, which takes two parameters, a and n. So we write the first base case. If n equals to 0, just return 1. That's the first base case. And for the second base case, if n is greater than 0 and n is an even number, that is n modulus 2 is equals to 0, we just multiply the half of the calculation with itself. First, we need to find the half of the calculation. That's what we are doing here. Half of the calculation is equals to binary exponentiation, which is calling the function again recursively, but with half of the n value. And we return a power n by 2 times a power n by 2, which will give us a power n. If it's neither of these two cases, it results in the last case, we don't have to explicitly write the condition. So we calculate half calculation just like before, but with subtracted n by 1, because n is an odd number now. It's pretty much the same thing. Let's try this function. Let's try the values of, how about 2 power 5? What is the value of 2 power 5? 32. Yes, seems right. What about 3 power 5? 243, which is correct. It in iterative way. Well, iterative way is a bit tricky because we treat the number as if it's in binary form, which is zeros and ones, instead of it is in decimal form. So let's initiate the result to 1 and check if the power is greater than 0 or not. And as long as if the power is greater than 0 and if the bit exists, we check it from left to right. Do you remember we represent 15 in the binary form as 1 1 1 1? So basically we are going through each bit and check if it's 1 or 0. So if it's 1, the bit exists, and if the bit exists, we just multiply result with a. So initially the result is 1, now it's a, and we multiply a with itself because the next bit is 2 to the power itself, right? 2 power 4 to power 8. Same way, we just multiply a with itself for the next bit, and we go to the next bit and return the result after this while loop or whatever this loop we used to complete it. Let's look at the code for better understanding, and let's look at the implementation. We just create the function just like before, which takes two parameters a and n, and initialize result to 1. And if we check if the number is greater than 0, that is all the bits in the number are not zeros, we can check if a bit exists or not by and operating with 1, because 1 and 1 is 1 and 0 and 1 is 0. So basically we and operate n with 1. The n here will automatically takes the first bit, and if the bit exists we multiply result with a, and we increase the a value exponentially for the next bit, and we right shift n to go to the next bit, and we return the result of the while loop. Well, the iterative way is a bit tricky to grasp, but if you dry run it yourself, you'll understand it. Uh, the fact that checking bits and working with bits is a bit tricky, right? And 3.15 is indeed the value here because I checked it in calculator.